our objectives for today.
At the end of this video with some practice, one should be able to recall solving for the roots of a polynomial equation, understand the complex conjugate root theorem and quadratic surd roots theorem, and lastly, form the polynomial equation given its roots.
Before we move on to the steps, let's clear up some terms and theorems, and also we'll be learning two new theorems. First, let's clear up some terms. Roots are when you can substitute with a variable x and it will make the equation or statement true. On the other hand, degree is the highest exponent of the equation. Do you remember the fundamental theorem of algebra? Well, it basically means that the degree of an equation is equivalent to the number of roots you can have.
Now we have the quadratic surd theorem. Basically, every irrational number comes in pairs. So, if with the quadratic surd root a plus b of a polynomial, a is a rational number and b is irrational, then a minus b is also a root of the polynomial equation. As for complex conjugates root theorem, it states that complex numbers come in pairs as conjugates. In essence, if complex number a plus bi is the root of a polynomial equation, then a minus bi is also the root of the same polynomial equation. So getting the polynomial equation from the roots is actually pretty simple and much easier and shorter than finding the roots of a given polynomial equation, as we only have to solve for one side of the equation. This means that the polynomial equation will always equal to 0.
The first step is to figure out the degree of the polynomial equation. Remembering the fundamental theorem of algebra, we know that the number of roots equals the degree of the equation. So the question now is, how many roots are there? This is almost as simple as just counting how many entities there are for the x variable. But as you are counting, remember the quadratic surd theorem and complex conjugate theorem. The next step is getting the binomial factors. In this, we just do a sort of reverse zero product problem. Remember how if you equate each binomial factor to 0, isolate the variable, you can get the root. Well, it's the same concept. For every x is equal to c being a root, and knowing that x minus c is the formula of the binomial factor, one just has to transpose c to the side of the variable, making it x minus c is equal to 0, which is the formula of the binomial factor. So now, we have the binomial factors of the polynomial equation. All you have to do now is multiply.
Let's try to solve this problem. Form a polynomial equation given the roots -1, 1 over 2, and 3. So from the problem, we know that x equals -1, x equals 1 over 2, and x equals 3, which means the polynomial equation has a degree of 3 because there are only 3 roots. The second step is to get the binomial factors from them by doing a reverse zero product property. So we transpose the c value so it equals to 0. From x equals -1, we now have x plus 1 equals 0. From x equals 1 over 2, we multiply everything by 2 to get 1. Then we transpose 1 and get 2x minus 1 equals 0. From x equals 3, we now have x minus 3 equals 0. So now we know that our binomial factors are quantity x plus 1, quantity 2x minus 1, and quantity x minus 3. We can put them together and they become quantity x plus 1 times quantity 2x minus 1 times quantity x minus 3 equals 0. Now all we have to do is multiply. Let's try something a bit more difficult. Perhaps something with one of the new theorems we taught you earlier. Form the polynomial equation with rational coefficients in its lowest possible degree given the roots square root of 2 and I square root of 2. The first step is to figure out the degree of the polynomial equation. Now don't get all high and mighty if you think the degree is 2, because boy, are you wrong. The degree is actually 4. Why, you may ask? Well, let's list down the roots. If you thought the degree is 2, then maybe you should rewind and listen to us teach you the theorems again. Don't you remember that complex roots come in pairs? The next step is to get the binomial factors of each of these roots. Put that together and you have quantity x minus square root of 2 times quantity x plus square root of 2 times quantity x minus I square root of 2 times x plus I square root of 2 equals 0. Now, the multiplying part may seem simple, but when dealing with roots like this, it gets kind of tricky. Using special products, we will now multiply them. Now for a challenge. It's okay if you don't get this in a snap, but check this out. The challenge is to form the polynomial equation with rational coefficients in its lowest possible degree given the roots 1 minus the square root of 2 and 1 minus I square root of 2. So first we have to identify the degree of the polynomial to make our lives a bit easier. We'll base this on the quadratic surd root theorem and complex conjugate root theorem. So we'll end up with 4 binomial factors. That's because we were given 2 roots which both come in pairs. Second, we have to get the binomial factors for each root. So we transpose the roots to where the variable x is. You may wonder why it is called a binomial factor when there seems to be 3 terms, but that's because I and the square root of any number are complex numbers. Now, what I like to do is horizontally multiply. It's like the FOIL method. If you know the principles for that, this should be extremely easy.
Here's a summary of all our steps. First, get the degree of the polynomial equation by finding the roots. Then, remember the quadratic surd theorem and the complex conjugate root theorem. Next, get the binomial factors by applying the zero product property and simply multiply your binomial factors to each other. Then, simplify your polynomial equation and make sure that the last term is constant or a term without a variable. That's it!
That's all the steps to it, as simple as that. Don't forget to practice always since you'll be able to master the topic in no time. We provided 3 extra questions in the end of the video and all the questions will be in the description below. See you next time! Bye!